The last thing we're going to take a look at is finding function values and graphing square and cube root functions. So again, recall with our function values, the function, when we're evaluating something like f of 9 or f of 11, those just become replacement values for x or whatever our independent variable is. And so we can evaluate the function. Now notice it says we want to find the exact value as well as an estimated rounded value. So we're going to provide both. If we end up with a perfect square or cube, the exact value will be completely simplified and there's no need to round it. But if it's not a perfect square, we can identify the rounded value. So for f of 9, we'll go ahead and substitute 9 into for x in our equation. 9 minus 5 is 4, and we can take the square root of 4, and that's already completely simplified, so there's no need to find a rounded value. A different highlighter for when we do have rounded values. So we'll do f of 11, apply the same process, the square root of 11 minus 5, which gives us the square root of 6. 6 is not a perfect square, so that is our exact value. But then we can go ahead and take the square root of 6 by plugging that into our calculator. And when we evaluate it on our calculator, we get 2.494489743, something. And so what we want to do is round it to one decimal place, so we'll cut it off short at 2.4, and that is the rounded value for our solution. So you need to pay attention to any rounding directions that might be present in the problem. For g of x, we'll apply the same process, but with our new function, where we have the cube root of -2 plus 3. That equals the cube root of 1, which is just 1. So we have this exact value, no need to find a rounded solution. However, if we go ahead and take the cube root of 3 plus 3, we have the cube root of 6. Now 6 is not a perfect cube, so that's our rounded value, but now we need to go ahead and find our estimated value. Our calculator evaluates it to 1.81712, so on, and so we're going to cut it off at one decimal place at 1.8. Now let's look at domain. We're going to ask ourselves a question. So we're going to consider the radical function f of x equals the square root of x. And we want to think about what is x not allowed to be, and the function still equal a real number. And so with the x, with the radical expressions, with a variable, our radicand cannot be 0. So in this case, cannot be less than 0. X cannot be negative. So that means that our domain is going to be all possible replacement values for x. And since our index is even, that means the domain is a set of all non-negative numbers, meaning our domain is 0 to infinity. Those are the all non-real numbers. Now, as we add to the expression under the radicand, then our domain is going to change, because it's not that x can't be negative, it's that the radicand can't be negative. And so as we take stuff to an increase or decrease, add numbers and expressions and values to our radicand, then it's more an idea of, well, what values of x would keep our radicand non-negative? And so it's not going to be 0 anymore, it's going to be some other number. And so the easiest way to do that is to take your radicand and set it greater than or equal to 0. And that will tell you what your domain has to be. Now, if we're dealing with our odd indices, the domain will always be the set of not all real numbers, negative infinity to infinity, because there's no limitation on the radicand for our odd degrees. So let's take a look at this first function. We're going to set the radicand greater than or equal to 0 to find what our domain is going to be. When we isolate x, we find that x has to be greater than or equal to 2. That's the smallest value that x can be. X has to be from 2 to infinity. And let's prove that. Let's pick a number outside the domain, such as 0. 0 is a nice easy number. If we try to evaluate f of 0, 0 minus 2 is negative 2, and the square root of negative 2 is non-real. But if we evaluate f of 2, which we say is our starting point, we get the square root of 0, which is the smallest non-negative value. So 2 is inside our domain. So once we know our domain, then we can set up an xy chart and we can get some points so that we can graph our radical function. So we know that 2 is our starting point and it gives us an output of 0. And then if we plug in a number like 3 and we evaluate f of 3, the square root of 3 minus 2 is the square root of 1, which equals 1. So 3 works. 3 is good, and it will work for all values greater than 2. Now, f of 4, we'll see it start to get a little interesting. We have the square root of 2, which is going to be a decimal approximation. Now, the square root of 2 is approximately 1.4. Well, that's kind of an annoying number to graph, since we have an approximation. So when we're trying to identify values of x, we want to consider what values of x will make my radicand end up as a perfect square so that I can take a nice even root. And so let's take a look at some different options that we could choose. If we do 5 minus 2, that gives me 3. 3 is not a perfect square. If I do 6 minus 2, that gives me 4. 4 is a perfect square. So if x is 6, the square root of 4 is 2. If we do 7, 5 is not a perfect square, 6 isn't a perfect square, 7 is not a perfect square, 8 is not a perfect square, but 9 is. So if we use x as 11, then the square root of 9 is 3. And so now we have much easier points for us to graph. So we can graph the point 2, 0, 3, 1, 6, 2, and 11, 3. And as we see that if we plotted the 4, 1.4, it ends up in about the same spot for our curve. And so we see that slowly, that arch that rises quickly and then levels off very soon being formed, which matches our parent function that we saw in an earlier chapter of the square root function. Notice how it doesn't go to the left at all, because when we tried to plug in a smaller number like 0, we got a non-real number, and I can't graph non-real numbers on the Cartesian grid. Now, our cube root functions are a little bit different, because like we mentioned earlier, the domain is going to be all real numbers. Negative infinity to infinity, so x can be anything. So again, we want to consider values of x that will make my radicand a nice even, not an even, but a perfect cube so that we can get an integer rational value for our ordered pair. And so let's think about some numbers. If I use 0 for x and I add 4, I don't get a perfect cube. If I add 1 to 4, I don't get a perfect cube. 2 gives me 6, 3 gives me 7, but 4 gives me 8. So if I substitute 4, the cube root of 8 is 2. Now I'm going to run out of room on my graph if I keep going up. So remember, we can also go down. Instead of doing 0, we can do negative 1. Negative 1 plus 4 is 3. That's not going to work. But let's go a little lower and say negative 3 plus 4 is 1. And the cube root of 1 is 1. So negative 3, 1. Negative 4. The cube root, negative 4 plus 4 is 0. So if we use negative 4, we get 0. If we do negative 5, the cube root, so negative 5 plus 4 is negative 1. So the cube root is negative 1. And we can even go further to negative 12. The cube root, negative 12 plus 4 is negative 8. So negative 12 gives us a cube root of negative 2. And so let's plot those points. We start at 4, 2. That was our first one here. And then we go negative 3, 1, negative 4, 0, negative 5, negative 1, And it's going to be a little bit off the grid, but we've got negative 12, 2. And we see in this part here, we kind of have a straight line, but then we have that bend going off to the side. So that means that we're going to start here, and it's going to model our square root curve that we have up here, but then it does the opposite direction in the other direction. And this is going to be the general shape for all of our cube root functions, and as a matter of fact, for all of our odd index functions. Well, this is our general shape for all even index functions.